ways to prevent cold gas from reaching disks and fueling star formation, but I want to talk about ways that it's possible to just suppress the star formation in the presence of fuel, right? We've seen that there is cold molecular gas in elliptical galaxies, and so what I'm showing today is the role that dynamics can play in suppressing star formation in a gas reservoir. So the idea here is, picking up where Marie left off, is not necessarily that we're talking about quenching, we're talking about regulating star formation, and this might be important for tuning the feedback knobs, right? Maybe this is a way to adjust the amount or the degree of feedback that is necessary. So yesterday, during Nick's talk, it was clear that we really still haven't converged on what is the Kennecott-Schmidt star formation relation. So let's first start off by thinking about the physics behind the Kennecott-Schmidt. So we've seen this a few times. This is log of the star formation rate surface density against the log of the molecular gas surface density. This is the molecular Schmidt law, right? And what we see is, like we've all heard before, we've all read in our textbooks, this is a power law relation over many orders of magnitude linking normal disks with starbursts. And this is the first indication, or provided the first indication, that what's happening on the scale of clouds is important for star formation. And the reason why, right, is that, let's say that molecular gas is converted into stars in some time scale tau. Well, the fact that we see a power law relation and the power law index is about 1.5 tells us that this time scale is something like the cloud freefall time, which goes like 1 over the square root of the volume density. That's very hand-wavy, and we've since learned better, but it's interesting, right? So maybe what's happening on the scale of clouds is important for star formation. But of course, we now know that this isn't quite what things look like in nearby local galaxies. So each point here is from a 1 kiloparsec sized aperture in one of, say, 15 to 20 galaxies. And what you see is a linear relation between the star formation rate and molecular gas surface density. And so, as Nick says, well, maybe the job is done, right? All we need to know is how much molecular gas there is, and you can count how many new stars will form. It's amazing, right? We have this nearly linear relation, and what it implies is that there looks like there's a constant molecular gas depletion time. Constant molecular gas depletion time maybe says, well, maybe there's a universal cloud. Maybe all clouds have the same freefall time, right? So keep that in mind, right? Maybe all clouds have the same freefall time. But
that's not inconsistent with the previous plot, I think, is it?
Well, so the previous plot did imply that there was not a universal depletion time.
Much larger range.
That's right. And maybe there are two regimes. Yep. Okay, but one thing that I'd like to highlight is that there's a good degree of scatter here in this relation. So much scatter that you can have very short molecular gas depletion times and very long molecular gas depletion times. We're talking about an order of magnitude variation in the depletion time. And so then it's not just as simple as saying that there is a linear relation between molecular gas and star formation. So let's ask, what is the source of the scatter? Well, there's a couple of ideas, and we've learned a lot about the scatter by looking at its scale dependence. So if we probe smaller and smaller regions in nearby galaxies by going to higher and higher spatial resolution, we see that the scatter booms, right? So this box down at the lower right was what I showed you in the last plot. So this is now contours of those data points now probing to smaller and smaller spatial resolution, or higher and higher spatial resolution in one galaxy, M51. Right? And so then this suggests that maybe, well, there's this two modes of star formation business. I don't have time to go into that. But people are starting to think, well, maybe this is because of discreteness and stochasticity, right? I've got my little region, I've got some stars, I've got some clouds, and depending on the size of my aperture that I plonk down, I'll be sampling the stars and the gas maybe differently.
No, but we know it's a time.
Absolutely.
Sure, there's a time progression because you're waiting to the final spatial and temporary scales of going.
Yes, and I think that that's part of what I mean by discreteness and stochasticity. So what Nick is alluding to is the fact that observationally, right, there's a finite lifetime with which we can associate our star formation tracers, right? And in that time, we have destroyed clouds, we have spatially offset the stars from their birth clouds, this kind of thing. So that all goes into the scatter, right? This is one idea, right? So you plunk down your aperture, you sample things differently, you can increase the scatter as a function of spatial scale. I think I'm going to add one more thing to this, and that is really galaxy dynamics. So it's not just an observational thing. There really are variations in the depletion time because of dynamics. And it has to do, I think, with the fact that only some clouds, some of the molecular gas will form stars. That ratio of actively star-forming molecular gas versus inactively star-forming gas changes, and it depends on the dynamics. So, in fact, I think that the same large-scale processes that we normally associate with fueling the centers of galaxies is actually also causing this change in stability of the gas. So from large scale, right, we have this idea that torques drive large-scale gas motions in disks. These are really handy for bringing gas, newly accreted gas, which falls in the outskirts of galaxies, all the way into the centers, right? But at the same time, as this gas is moving in, it can be stabilized. Some of the gas can be stabilized, shut off from forming stars. I would call this a sort of an effective feedback, right? Other clouds can be sheared because of the dynamics, right? I'll show you that that can limit the lifetimes below the freefall time, shutting off, again, the potential for clouds to form stars. Now, of course, some of the gas that's lucky enough to not have formed stars, if you want to say it like that, makes it into the center to go on and fuel the growth of the black hole, and then we get all of our favorite feedback, right? So, of course, this is going to be my outline, effectively, for today. And since I was asked to talk about observations, I'll, throughout the talk, highlight where high-resolution molecular gas observations have really been key to assembling this picture. So let's begin with the torques. So these are gravitational torques exerted on gas by non-axisymmetric perturbations to the underlying gravitational potential. We're all familiar with these in the context of mergers and interactions. For example, in this model, we've got tidal tails during the encounter between the two galaxies. These tidal tails supply gas to the centers of galaxies. You get your starbursts, you feed your black hole. As a result, in the end, you get something that is resembling an elliptical galaxy. But we also have, in the local universe, tons of non-axisymmetric gravitational perturbations in the form of bars and spirals, right? Now that's in the present day, and I think that probably at intermediate redshifts there's a mix between the really strong stuff you get in mergers and interactions and some of this well-defined structure that we see today. But I think we can guess that a lot of these structures exist. So in any case, I'm going to use what we know about non-axisymmetries in the local universe to understand something about the way that gas is moved around in galaxies. So if you think you can map the stellar mass distribution, so in this case I've done it from 3.6 micron images, then you've got your stellar mass distribution. It's trivial, well, sort of trivial, to calculate the gravitational potential, and from the gravitational potential calculate what your 2D map of torques is, right? That's just R across the gradient of the potential. So here, in the case of M51, I'm showing you the torque map with the CO contours overlaid in red. Everywhere you see white here corresponds to a positive torque that will cause gas outflow, and black here is negative torque, which, energy and angular momentum will move outward, gas inflow is driven inward. Now from this 2D torque map we can make something that's really handy, and that's the azimuthally average radial torque as a function of radius, shown here for this case down below. And again, you get, black is showing negative torques, white is showing positive torques. Now this has been really handy for interpreting just basically the link between dynamics and morphology in all sorts of nearby galaxies. So for example, when we see the torque change from negative to positive, we can associate that with the end of the bar in this, there's inflow. Here's the end of the bar, and that matches perfectly with what we see. The other transition from negative to positive actually tells us where the co-rotation radius of the spiral is. This is great. And then when we go from positive torque to negative torque, then actually we start to get opposing torques and we can get the pileup of gas. Okay, so this is really cool, and I don't want to go into too many details. Let me just step back and remind you then again that what these torques do is they drive non-circular streaming motions that look something like this in the case of M51. These motions are directed along and through the spiral arm, and they can be big, right? So here I'm showing you streaming motions that are larger than the gas velocity dispersion shown in the dotted line, and they can be as large, they can be as large as 20 to 25, 30% of the circular velocity in the disk. These are not negligible motions. Now, critically, our view of these non-circular motions depends a lot on how we trace them, what particular tracer we use. So this is something that our student Dario Colombo looked at in really good detail. So here are the magnitude of spiral streaming motions as a function of radius in M51, as determined directly from the CO observations at 1 arcsecond resolution, and then those same observations smoothed 6 arcseconds, which is exactly the same resolution for which we have the H1 observations. And you can see that at exactly the same resolution, the streaming motion magnitude is different. And the reason why is that the H1 and the molecular hydrogen have different distributions. We know that molecular gas is clumpier than atomic hydrogen. It's denser, it's confined more to the midplane of galaxies, it feels the potential differently. The H1 is generally sitting in a puffier disk. It feels a weaker potential.
But it's also more concentrated as grand spirals.
Well, so oftentimes what we see is that the molecular hydrogen is really sitting right in the minimum of the potential, and the H1 is sitting a little bit offset, right? Exactly. So this is why in particular here we see the difference in the streaming motions. Yeah. Okay, so now I think I've convinced you that, yeah.
I'm a bit confused how you measure this, because the streaming motions, even if at a given radius, azimuthally, it will also vary, right?
Yes.
So is this an azimuth average, or
This is
at the spiral arms, or?
This is at the location of the spiral arm. This is where the m equals 2 is at maximum.
Okay.
Okay, so yes, so I've convinced you now that if you want to really probe the potential locally, you want to be looking at molecular hydrogen. But you want to also be looking at molecular hydrogen in high resolution, of course, because the structures that we're interested in probing are pretty tiny, right? So this is our view of M51 about 5 years ago, and you can see that the spiral arm itself is just resolved by the observations, by the size of the beam. This is, of course, our view of M51 today. Many of you have already seen this. This was a major effort to map CO1 to 0 emission across the central 9 kiloparsecs of M51 with all of the two main facilities of IRAM. The PI is Eva Schinnerer, and what we've done is a very detailed set of papers to analyze the way that the molecular gas is distributed. So in M51, I should note, the ISM in this zone is molecule dominated. The CO is a tracer of the gas mass, right? And what you can see here is that the spiral arms are not smooth. They're actually composed of very discrete structures. And even in the interarm, you can see all of these little knotty discrete clouds, right? And our student has decomposed the CO emission into a catalog of over 1,500 clouds. Now, my favorite aspect of these observations, of course, is the velocity information that we get. So here's the line of sight velocity field in this area, and what you can see are very, very large streaming motions, the same streaming motions that I showed you profiles of earlier. So for reference, this is the line of sight velocity field for a galaxy undergoing circular rotation, right, circular motion, projected on the sky plane at the same orientation as M51. You get a nice smooth velocity field, but the real thing looks nothing like it. And you can now see, I think, a little bit clearer just how these streaming motions are associated with the bar in the center and then the spiral arms.
But non-circular motion, I mean, if I have a non-axisymmetric perturbation, right, any orbit, a regular orbit will now become, instead of circular, will become like elliptical.
Yes,
right?
so there's both
if the gas is just moving on closed elliptical orbits, you would infer at any given point this non-circularity in the motion, but that's not a streaming motion in terms of that it's a torque-induced motion.
Well, remember the gas is dissipative. So it is.
But molecular gas could be in clouds that, could in principle be ballistic particles.
I don't think that they're ballistic.
I'm not saying I do.
I don't think that they're ballistic, but you can see that there are non-circular motions, and it has to do.
Not necessarily torque-induced streaming.
Well, I think that it is streaming motions. If you were to compare the stellar kinematics with the gas, you do see that there's a difference.
But you also have diffuse components, yes.
Yeah.
And that will not go on.
That's right.
So
Let's not talk about the diffuse component. If you want to ask me about it after the talk, fine. Okay. Oh, shoot. So I guess I better move on here. I haven't even gotten to the good stuff yet. But you could see here that the spirals are really driving all of these these large streaming motions. And so what they're doing, the spiral arms, is they're organizing the gas. And they're also structuring it down to the molecular cloud scale. So there was this idea, right? The streaming motions build up high gas densities, and when you have high gas densities, you can form a lot of stars. Spiral arms are also thought to be the sites of reduced shear, and this is all supposed to encourage star formation. And then all the way down to the giant molecular clouds themselves, we can see that the spiral arm is playing a role. And that for the first time because of our pause observation. So let me quickly review that. With our catalog of clouds, we've been able to construct mass spectra, cloud mass spectra, in a series of dynamical environments. And this is thanks to the large number of statistics in our cloud catalog. So region by region, center, spiral arm, interarm, I'm going to show you the shape of the mass spectra. And you can see that it's changing from interarm, which is in green, to spiral, which is like blue and purple here. And also the number of clouds is increasing, right? We get more and larger clouds in spiral arms. So this is consistent with spiral arms, growing clouds through collisions and agglomeration, but also building up the densities that reduces the gene's length, and so you get more clouds in your spiral arm. Okay, that's great. We also have looked at the scaling relations for clouds, and the scaling relations are sort of the backbone of our interpretation of the Kennecke-Schmidt relation. I don't have time to go into them, but there's several papers on them by now. I just want to note the takeaway, which are that clouds in spiral arms are brighter, they're more massive, and they have higher gas surface densities than clouds in the interarm. Now, the higher gas surface density should be making you think, Kennecke-Schmidt, right? Because I said that it looked like all clouds have the same freefall time, that is, they all have the same surface density. But in fact, they don't. Okay, so, I really don't have much time. Now that we've seen that there is no universal cloud, clouds know about their environments. They know if they're in the interarm compared to the arm. And how is that possible? How is it that clouds inherit their properties from their surroundings? Well, again, I think it goes to the fact that clouds are not decoupled from their surroundings, right? They inherit their properties from the surroundings. And we've just looked at the internal versus the external pressure in clouds in M51 and a whole bunch of other galaxies, and we see that they're in near equilibrium. I'm not saying that they're identical, but they're close enough, right? And so somehow, clouds inherit their properties from their surroundings. Now, I think that this near balance between internal and external pressure is also telling us something important about the stability of clouds. If we perturb what's happening on the surface, we could really make the difference between stability and collapse. So this led me to develop this picture of dynamical pressure. So I'll try to go through it quickly. Some of you have seen it enough already, but I'm sure that there will be questions about it. So the idea is that you've got, gas, it's rotating around, the center of the galaxy is somewhere down on the left. Now I'm going to introduce my spiral arm, and as a result, I have a change in my gas velocities through the spiral arm. Now, Bernoulli tells us that when I increase the velocity of the gas, it exerts less pressure. So in this little graphic here, it's not supporting against the boundaries of the tube anymore, right? So I've got less pressure in my gas. As a result, the clouds that are embedded in that gas feel less pressure on the surface. Now there's less helping gravity, right? As a result, let's say that there's an increase in the cloud stable mass, so clouds can be way bigger before they collapse and form stars, and as a result, you get a lengthening in the gas depletion time. This is the idea. Now, do we see something? Let me just skip back. That's my little graphic.
Well, the problem is this, Sharon, right?
Yeah.
That the spiral arms in M51 is tending to waves. So you don't have it, you shouldn't have much jumping.
You do, but we see that there's an offset between the potential minimum and the CO, and the gas is being torqued. So there are these motions, yeah. Now granted, you're right. This may not. Thank you. Is that 0 or what? Okay. Well, let me continue. So now if we put I've measured molecular gas surface density, star formation rate, surface density, and a whole bunch of rings in which I know what the spiral arm steering motion is at the location of the spiral arm. And what you can see is all of the regions where the streaming velocities are high are sitting preferentially at the longest depletion times, and where there's small gas streaming velocities, you've got shorter depletion times. Now let me just show you this face on so you can see exactly what I mean. Those green points from the previous plot come from these rectangles here. You've got plenty of molecular gas, right? You've got as high a gas surface density as you have elsewhere along the spiral arm, and yet we see very little massive star formation. So here's the FUV picture. You can see in those rectangles it's blank. And it's also obvious that there's a lack of massive star formation when you look at the dust obscured component, so traced by 70 microns. So as a result, right, we saw that the depletion time varies a lot, and in between those two green lines is the long depletion time. So I don't have too much more time. It looks like I have to end. I'm not saying that star formation doesn't occur near spiral arms. I'm just saying that it doesn't happen as efficiently as it could because of these motions. And I guess, yeah, I don't have time, but the idea here is that the stronger the spiral, the stronger the streaming, more suppression in the star formation, right? And I would, let me just show you that again. I think that this holds not just in spirals, but also explains the lack of star formation that we see in bars. This is a well-known phenomenon. You can see here in NGC 4303, the dust lanes that run along the bar have no massive star formation. Okay, so I guess I've got to stop, but I just wanted to mention that now we've been applying this to interpret the variation in the depletion time along the Hubble sequence that we do observe, and we're also now working to think about how this relates to the suppressed star formation that we see in the centers of elliptical galaxies. So my takeaway, not all cold, dense molecular clouds form stars. Dynamics regulates the organization, the structure, and the stability of molecular gas. And some food for thought, the same large-scale processes that fuel the centers of galaxies are also suppressing star formation. So they're happening at the same time. So, thank you.
Two questions.
I'm a bit confused with the Bernoulli argument. I mean, you're talking about the gas when it comes close to spiral arms speeding up. Is that?
Yeah.
So first of all, I don't see why it would necessarily speed up. And the second thing is, I can see that it works. If that's the case, then it might work, but only if the pressure inter-arm and outer
Right.
out of the arm,
You mean that?
are the same, because if there is already pressure enhancements
Yeah.
when you enter arm, that would
Yeah.
counter.
So, if I've looked at the compressible Bernoulli, which does take into account the fact that the stellar surface density increases through the arm, and that's negligible compared to this change because of the velocity difference between the arm and the interarm. But in any case, yeah, your point about the streaming is right. What I mean is relative to the underlying rotating potential.
Nick?
Oh, I think last time we discussed this, I thought it was very upsetting for going serious. I lost 5 pounds not worrying about this after that. But after all, F51 is just one galaxy, a very
Yes,
special one.
yes.
Because the spiral arms are not only grand design, they're also standing great, which is probably very, very rare. So then
No. Okay.
Maybe.
Okay.
Then it's kind of, it's not a very practical, constructive question. So basically, I think I hope to do it for galaxies which are sort of more regular.
Yes. Yes, I would love to devote some time, the time of a student maybe, onto a project like this. But yeah, I mean, I think that's exactly what needs to be done. Now, we do have some cycle 1 ALMA observations of another grand design spiral galaxy coming in. It's not as grand design as M51, but yeah, I think that's exactly what we need to do. We know how to measure streaming motions. The tools exist, and it should be trivial to just go ahead and measure the depletion times, plot them against the streaming motions, and show.
No, it's not real to get the data.
No, yeah, thank you. Yeah, that's not. Yeah, but I think that would be really very nice. And all that I've been working with so far are the global measurements that exist and trying to interpret them in this
All right,
light.
sorry, I think I have to cut the discussion here. Let's thank Sharon again.